Okay, so you ever fire up a brand new game, like crank those graphics settings up
Yeah.
to like Ultra Nightmare just to see what your rig can actually handle?
Oh, yeah.
And then, you watch as the action just slows to a choppy crawl.
Yeah, I've been there.
Yeah, we've all been there. But then you enable DLSS,
Right.
and suddenly, buttery, smooth gameplay, visuals, crisper than, I don't know, a freshly printed dollar bill.
It's like magic.
It feels like some next-level sorcery, right?
Yeah, it's definitely some impressive tech, no doubt about it. And that's exactly what we're diving into today. We're going to really dissect the NVIDIA DLSS Programming Guide to give you like the inside scoop on how it all works.
Okay, cool. So for anyone listening who hasn't had the chance to experience this DLSS magic firsthand, what exactly are we talking about here?
So in the simplest terms, think of DLSS and an AI-powered graphics card upgrade, basically. It uses like the power of machine learning to take lower resolution images.
Oh.
You're playing a game and it intelligently upscales them to higher resolutions.
Oh, interesting.
And the really mind-blowing part, it does all of this while often making the image quality even better than the original, not worse.
Okay.
Which is, yeah.
That's what I call a win-win.
Yeah.
High resolution, A&D, smooth gameplay. Sign me up.
Yeah, right.
But how does it actually work? What's going on under the hood to make this magic happen?
Well, let's crack open this programming guide and take a look. First things first, DLSS isn't like some magic sprinkle you can just toss onto any old game engine, right?
Right.
It needs a specific foundation to work its magic, and we're talking about engines built on DirectX 11, DirectX 12, or Vulkan.
So those are like the big leagues of game engines,
Yeah.
right? Cutting edge, bleeding edge.
Exactly. And there's a good reason for that. DLSS needs very specific data from the game engine's rendering pipeline to actually work its magic.
All right.
This includes things like color information, depth information, which is basically a blueprint of the 3D scene, and most importantly, something called motion vectors.
Motion vectors.
Yeah.
Okay, time to put on our graphics programmer hats, I guess. What exactly are those, and why are they so important for DLSS?
So think of it this way. Imagine your DLSS, right? And you're trying to paint a super sharp picture from a blurry one. Motion vectors are like little arrows on each pixel telling you which direction things are moving between frames. So instead of just guessing how to make the image sharper, DLSS can use these motion vectors to accurately track the movement of objects.
Oh.
And it results in a much cleaner and more natural looking image.
Okay, so it's using information about movement to create a better final picture.
Exactly.
Clever. Now, the guide also mentioned something called subpixel jitter. And I'll be honest, that sounds a bit more like a medical diagnosis than a graphics term.
Right.
What's the deal with that?
Yeah. It's all connected to how DLSS creates those super sharp images. So remember, it's upscaling from a lower resolution, right? So imagine looking at a grid, and each square on that grid is a pixel. Subpixel jitter is like slightly shifting that grid with each frame, creating extra sample points that fall between the original pixels.
So it's like DLSS is creating extra information out of thin air.
In a way, yeah. By analyzing these slightly shifted images over time, DLSS can actually extrapolate what the missing pixel should look like.
Oh, wow.
And that results in a much higher resolution final image. It's like having like a 1080p display suddenly act like a 4K display.
Okay, that's starting to sound like that magic we were talking about earlier. But the guide stresses that this jitter has to be done in a very specific way. Something about a Halton sequence being super important. What's that all about?
It's all about making sure those subpixel jitters are spread out in the most efficient way possible. The Halton sequence is a mathematical formula. It's not as scary as it sounds,
Okay.
but it helps developers create these jitter patterns. It ensures that the jitters are evenly distributed across the entire image, avoiding any weird clustering or artifacts that could negatively impact the final image quality.
So it's like the difference between like randomly throwing darts at a dartboard hoping for the best and strategically placing them to get like the highest score.
Exactly.
Okay.
Yeah. The Halton sequence gives DLSS the best possible aim when it comes to these subpixel jitters. And then speaking of aim, the the guide also talks about having enough phases for these jitters.
Yeah.
It's like having more arrows in your quiver, each pointing in a slightly different direction, which allows DLSS to capture even more detail and movement information.
More phases, better image quality.
Yeah.
Got it. This is all starting to make sense, but it sounds pretty complex to get right. Are there tools available to like help developers make sure they're implementing this jitter correctly?
Absolutely, yeah. There are, the guide mentions several debugging tools that developers can use to like actually visualize these jitter patterns. It's like having a special pair of glasses in a way that let them actually see these subtle shifts in the image.
Oh, interesting.
Yeah. This allows them to fine-tune those jitter settings and make sure everything's working in perfect harmony.
Okay. That's reassuring. I'm always a bit wary of things that rely on like mathematical formulas working perfectly in the real world, you know.
Sure.
But it sounds like the developers have some good tools at their disposal.
Mm-hmm.
So we've got the motion vectors, we've got the jitter down. Anything else developers need to pay like really close attention to when it comes to DLSS integration?
Yeah. There's one more crucial ingredient we need to talk about, and that's exposure.
Okay.
You might not think it's a big deal, but DLSS needs accurate exposure values from the game engine, especially when dealing with HDR content.
Okay, back up a bit. For those of us who haven't quite wrapped our heads around all the HDR jargon yet, what exactly is HDR and why is exposure so important for it?
Sure. Imagine you're looking at a sunset in real life.
Right.
You've got like the blindingly bright sun, but you can also, see details in the darker areas like the shadows and the clouds.
Right.
And that's what HDR tries to replicate in games. It's a wider range of brightness levels. So from the darkest darks to the brightest brights. Exposure basically controls how bright or dark the overall image is, and it's crucial for HDR content to look realistic and not washed out or overly dark.
So if the exposure is off, even with DLSS doing its thing, the image won't like look quite right, especially in those super bright or super dark areas.
Yeah, that's a great way to put it. It's like trying to bake a cake with the wrong oven temperature. Even with the best ingredients, the result's just not going to be the same.
Okay, that's a baking analogy I can get behind. So how do developers how do they make sure DLSS is getting this exposure information correct? Is it something they have to like manually tweak for every scene?
Thankfully, no. The game engine is already calculating exposure values for other effects like tone mapping, which basically adjusts the image's brightness to fit within the capabilities of your display. Developers just need to make sure that they feed that same exposure information directly to DLSS.
So it's more about like making sure the information is shared correctly rather than having to like create it from scratch.
Exactly. Yeah.
That makes sense. But what if the exposure is a bit wonky? Are there tools to help like diagnose that? We don't want our delicious HDR cake coming out of the oven burnt.
You're speaking my language. And yes, the guide talks about some really helpful visualization tools that developers can use to spot if the exposure values are off. They can see exactly which parts of the image are being affected and make adjustments accordingly.
Okay, that's reassuring. We've covered a lot of ground here.
Yeah.
Motion vectors, jitter, exposure. It seems like DLSS needs a solid stream of data to work its magic.
Yeah.
Now, I know some of our listeners might be thinking, this all sounds incredibly demanding. Won't this absolutely demolish my performance? What do you say to those folks?
It's a fair question. You might think something this sophisticated would require like a ton of processing power, right?
Right.
But here's the beauty of it. DLSS is designed to improve performance, not hinder it.
Hold on.
Yeah.
It's like having your cake and eating it too. It sounds too good to be true. Does the guide give us any hard numbers on what kind of performance gains we're talking about?
Absolutely. They have something called an execution technotable, which basically shows like on average how much time DLSS takes to do its thing on different RTX GPUs. And we're talking milliseconds here, like fractions of a second, even for the most demanding resolutions.
Okay, but realistically, most people are probably running this on like the latest generation of cards, right? What kind of performance are we looking at with, say, an RTX 3080 or even a 4000 series card?
Yeah, so for like a top-of-the-line card like an RTX 4090, DLSS it's basically instantaneous. We're talking microseconds.
Oh, wow.
And even on a more common card like an RTX 3080, DLSS upscaling to 4K resolution takes less than a millisecond.
Wow, it's crazy fast.
Yeah.
Processing entire frames in like the blink
Yeah.
of an eye. But what about VRAM usage? Doesn't all that AI magic gobble up memory?
Another great question. And the guide addresses that too. While DLSS does use some VRAM, it's surprisingly efficient. Plus, developers have access to a special function that allows them to see exactly how much VRAM DLSS is using at any given time,
Okay.
which helps them optimize their games and make sure everything runs smoothly.
So they can keep track and make sure DLSS isn't like hogging all the resources.
Exactly.
Clever. Now, I know this guide is mainly geared towards developers, but is there anything in there that our listeners, gamers like us, would find particularly interesting or relevant?
I think just like understanding how DLSS works under the hood gives you a much deeper appreciation for what you're seeing on the screens.
Sure.
You'll start to notice those subtle ways it enhances your gaming experience, and you'll understand why those system requirements are there. It's like being able to appreciate a magic trick even more after you know how it's done.
It's like peeking behind the curtain and seeing the wizard pulling the lever.
Exactly.
Speaking of wizards and magic, are there any particularly cool tricks or techniques mentioned in the guide that really highlight the power and the flexibility of DLSS? Something that makes you go, wow, I can't believe they can do that.
There's a section on something called biasing the current frame that I find particularly fascinating.
No, biasing the current frame. It sounds like we're about to step into some like advanced DLSS territory here. Do break it down for us. What's that all about?
So it's a technique that gives developers more fine-grained control over how DLSS handles certain types of tricky game elements.
Okay.
Think about things like particle effects, explosions, smoke, that kind of thing, or objects that are very thin or move incredibly fast.
Sure.
These can sometimes trip up even the smartest upscaling algorithms, or
Yeah.
they can lead to weird visual glitches or artifacts.
So it's like those moments in games where you see like strange trails behind objects or the edges of things look a bit fuzzy.
Exactly, yeah. Biasing the current frame essentially allows developers to tell DLSS, like, hey, pay extra attention to the current frame's information in these specific areas, and this helps smooth out those rough edges and reduce those distracting artifacts, especially for those tricky in-game elements.
So that's like giving DLSS a little extra guidance, I guess, to handle those edge cases where the usual algorithms might struggle.
Exactly.
That's really clever. It makes you realize how much like work goes into making these games look as good as they do.
It really does. And the best part is that techniques like this are constantly being refined and improved as AI and machine learning technology continues to advance. It's an exciting time to be a gamer and a game developer.
Speaking of developers, the guide also touches upon how developers actually incorporate DLSS into their games. It sounds like it's more than just like dropping in a file and calling it a day.
It definitely is. Yeah, there are specific libraries that developers need to include in their game's code, and the process needs to be handled, carefully to ensure compatibility and avoid any like unexpected issues.
The guide mentioned something about a debug library.
Yeah.
And the importance of making sure that's not in the final game release. I'm guessing that's for obvious reasons.
Precisely. The debug library is like a developer's toolbox in a way. It contains all sorts of diagnostic tools and extra information that are super helpful during the development process. But you wouldn't want those tools left behind in the final game.
Right. That makes sense. It's like accidentally leaving the blueprint for a magic trick inside the magician's hat.
Exactly. Yeah. It could impact performance or even reveal sensitive information about how the game works.
Right. So assuming a developer has followed all the guidelines, integrated DLSS correctly, dotted their I's, crossed their T's.
Right.
What's the end result? What's the magic that we as gamers get to experience?
So imagine firing up your favorite game, right?
Yeah.
and cranking all the graphics settings to the max, 4K resolution, ray tracing, the works,
Yep.
and having it run smoother than you ever thought possible.
Nice.
No more sacrificing visual fidelity for performance or vice versa. You get you get the best of both worlds.
It's like finally achieving that elusive balance in life. But seriously, that sounds incredible. And it's amazing to think that it's all made possible by this clever combination of AI, sophisticated algorithms, and some really dedicated developers. We've covered a lot of ground today, from the importance of motion vectors and jitter to the nuances of exposure and HDR. It's been a fascinating journey into the inner workings of DLSS. Any final thoughts for our listeners before we wrap things up?
I think the biggest takeaway is that we're just scratching the surface of what AI can do for gaming. As these AI models become even more sophisticated, who knows what the future holds, or maybe one day we won't even need traditional rendering pipelines anymore. It's a question worth pondering.
That's a mind-blowing thought.
Yeah.
It seems like the future of gaming is very, very bright, and AI is going to play a huge role in making it all happen. If our listeners want to explore DLSS further, maybe even try their hand at integrating it themselves, where should they go?
The full DLSS programming guide is available online, and there's even a sample code on GitHub to get you started. It's a fantastic resource for anyone who wants to dive deeper into this incredible technology.
Fantastic. We'll be sure to include links to all of that in the show notes. Thanks for joining us on this deep dive into DLSS. It's been an eye-opening experience for sure.
My pleasure. Until next time, keep exploring, keep learning, and keep pushing the boundaries of what's possible in the world of gaming.
I like it.